Hey everyone, it's Ken. In this video, I'm going to explain to you the statement of the second derivative test. And so what I want you to know about this is the content of this test is pretty much completely the same as the first derivative test. We're just rephrasing everything in terms of second derivatives. And so what this test does is it tells us when we find a critical point, is that a local minimum or a local maximum, or perhaps neither? And so let's just get right into it. So the setup for this test, the things that you have to assume that you're given a function f of x. You have to assume that you've located a critical point. And so critical point means that that's a x value c where either the derivative doesn't exist or the derivative is equal to 0. And in this particular case, for this particular test, we're just going to restrict ourselves to talking about when the derivative is equal to 0. So we're not going to be talking about those cases where the derivative doesn't exist. In fact, not only this, I need to know that the second derivative of the function exists and is continuous. That's CTS for continuous. So you need to know that at least the second derivative exists and is continuous, at least continuous on an interval around the point C. So on an interval containing C. And a lot of people in calculus textbooks leave that out, but I don't think this test is true unless you include that condition, and I'll explain why in a moment. So if this is your assumption, then what can you conclude from it? Well, what you can say is you look at the second derivative. That's why it's called the second derivative test. So you can say that if the second derivative at the point C is bigger than 0, then this critical point must be a local minimum. So f of c is a local minimum. And what's the reasoning behind that? Well, if your second derivative is positive at a point, and if your function is continuous, that means that when x values change, not so much, the y values change, not so much. So if you're positive at a point, then you must be positive for an entire interval around C. And on that interval, you must be concave up. So your first derivative must be increasing. So I'll draw like a schematic graph of your first derivative at the point C. Has to be 0 at C and then increasing, which means that the function itself needs to be concave up, or switching from decreasing to increasing, if you like, which means that you're going to have a local minimum at the point C. So this is the point x equals c, y equals f of c. And you see, you actually need the second derivative to be continuous, because you don't just want it to be positive at a point. You want it to be positive on an entire little interval. And so similarly, for the other case, if the second derivative is less than 0, then that's going to mean that f of c is a local maximum. And if the second derivative is less than 0, then that means you're going to be actually concave down on an interval, so that point's going to be a maximum. But to trace through the argument, what you do is you say if the second derivative is negative, then the first derivative has to actually be decreasing. So you're now switching from positive to negative. So you're switching from increasing to decreasing. If I draw a schematic picture of f, then now looks like that. And this point f of c is now seen to be a local maximum. So that's the second derivative test. When you find a critical point, check that second derivative. If it's positive, you're a local min. If it's negative, you're a local max. If it's 0, that's the other case we haven't handled. If it's 0, then you have no information. You have no information about what's happening. You could be a point of inflection, for instance, but you can't know whether you're going to be a local min or a local max. So a quick example of that, if you go back to y equals x cubed and look at the second derivative at x equals 0, then that's going to be a critical point with second derivative equal to 0. It'll neither be a min or a max. So that second derivative test only works when your second derivative is definitely positive or definitely negative at a point.